Now we can move towards drawing the shear force diagram as well as the moment diagram. So let's draw first the shear force diagram. Now we are familiar with this value, which is 31.5 kilonewton, and this is 7.5 kilonewton. So for drawing the shear force diagram, we should identify the regions in which the shear force will change. Like there is a region between C to A, there's no force there, so there won't be any change in the shear force. But as soon as we shift towards the region between A to B, because of the RA, there will be change in the shear force diagram. So we usually take the x distance from the left hand side. So let's say that the start point is C. So from here the x1 would be up to A point, and the x2 distance will be after point A. This we usually do when we have uniformly distributed load or uniformly variable load, but in this case there is no such load there, so we don't need these x1 x2 in our calculations. In this case the calculation will be quite simple. So let's say that this is the shaft, and on this shaft we are going to draw the shear force diagram. If we are on point C, because of 24 kilonewton force which is acting downward, the shear force will be exactly equal to that. So if you want to draw by scale, then accordingly you can choose the scale to draw that. So I just drawn roughly. So this has a magnitude of 24 kilonewton, and between point C and A there is no force there, so the shear force in this region will remain constant. But as soon as we will reach at point A, there is a upward force of RA, that is 31.5. so now this, because 24 kilonewton is downward, which is negative, now we have 31.5 which is upward, that is positive. We usually take the upward as positive and downward as negative in case when we are dealing with the shear force. So as a result of that, we will have 7.5 kilonewton as positive up till that point. So we will move by magnitude of 31.5. So this will be same 24 kilonewton plus the 7.5 extra from this side. And as you can see, between A and B there is no force there. So the shear force in between these 2 points will remain same. But as soon as we will reach point B, there is a force of 7.5 kilonewton at RB. So we will move downward by a magnitude of 7.5 kilonewton. So therefore we will coming back to the point where we have started in terms of x-axis. So this will also be then 7.5. So this is actually the shear force diagram. Now we just have completed the shear force diagram for the shaft. Let's move on for the bending moment diagram. Now when we were dealing with the shear force, there was no variability in between the points. Like in between C and A there was constant shear force. But in case of bending moment, since there is an involvement of moment arm, so if you are calculating the bending moment at any point, then at that point the moment arm will have some value. So therefore we need to take the variable in that case. So let's take the variable as x, that's starting from the left. So let's start from the left side. If we are at point C, since all the forces on the left hand side will be considered, so in case when we are at the C point there is no force on the left hand side, and if you are calculating the moment arm at C point, because the force is going through the point C, so there won't be any moment at point C. So we are having zero moment at point C. So now if we are in between point C and A, let's say over here, so then this will be the x distance. So in this region the moment will be calculated by the formula. So moment in the region of C and A will be calculated as 24 multiplied by the moment arm, and that moment arm is x. Let's say we are x distance away from the point C. And the other thing that you have to keep in mind, that's actually the sign. So this kind of bending moment will be anti-clockwise, so I consider that as a negative. So negative 24 multiplied by x. So the moment arm between C and A will vary linearly using this equation. So this equation is valid up to point A, and at that point we have the value of x as 250 millimeter or 0.25 meter. So if we want to calculate moment at point A, then it will be negative 24 multiplied by 0.25. So on doing calculations, it will be minus 6 kilonewton meter. So at point A, we have moment of minus 6 kilonewton meter, and as the moment between point C and A varies linearly, so there will be a straight line between these 2 points. So the slope of this variability of the moment is actually being calculated using this equation. So over here we have a magnitude of 6 kilonewton meter. Now as soon as we shift from the region of CA to AB region, so then in that case this equation will no longer be used. So the equation for the calculation of moment in the region of AB will be calculated as, then the x will be actually, it's up to you whether you want to take the x from extreme left, or maybe if you want to take x from this point, A point, it's again up to you. So let's say we are over here, and in most of the cases the x is usually being measured from extreme left side. So if we are, let's say, over here, and now the x is to this point, now the formula for calculating the moment in the region of AB will be, since all the forces on the left hand side will be considered. So on the left hand side we have 24 kilonewton, which is acting downward, Ra acting upward. So 24 kilonewton will have anticlockwise moment, so negative multiplied by x, and the Ra will have clockwise moment 31.5, half of momentum. Now momentum will be x minus this distance of 250 millimeter or 0.25 meter. So I keep it in meters. So simplifying this equation, we are going to have 7.875. Simplifying further, 7.5x minus 7.875. So this will be the final equation in the region between A and B. Now in this equation, if we want to calculate the moment at point B, so for that we know that the distance from C to B is 1.05 meters. So if we put here in this equation 7.5 multiplied by 1.05 minus 7.875, so when you do the calculations, we are going to get the value of 0 as the moment at point B. So if you look at the equation of moment that varies between point A and point B as a linear equation, so there will be a line that connects this 6.5 kilonewton meter point to point B. So slope of this is different, the slope of this line is different. So this line varies by this equation, and this line varies by this equation. So this is how the calculations for the bending moment diagram are carried out when we have this kind of situation. I made it a bit lengthy, but I believe that you will have a better concept regarding drawing the shear force diagram and bending moment diagram when we are being given with any kind of member which is being applied with the transverse loading, like the one in this case. The calculations are pretty simple, but again you need to be very concise with the minute details, otherwise it will lead to wrong calculations. So those minute things that you have to keep in mind. So now we just have completed this first problem related to the bending, the sixth chapter from the Mechanics of Materials book by the R.C. Hippler. In next coming videos we are going to solve more problems related to the bending, and I tried to make it simple as possible, but if you still feel there is something that you could not understand, then please let me know through the comment section. I'll try my best to get back to you. So that's all from my side. Thank you for watching this video. I hope to see you in next coming videos. Till then, bye.